right, the last example we're going to talk about in section 13.3, and actually all of chapter 13, is the idea of the law of diminishing returns. So in economics, the law of diminishing returns is related to the idea of concavity, which we've been talking about, right? We can find the concavity by looking at our second derivative. The function graph gives the output y from a given input x. So if the input were advertising cost for some product, for example, the output might be the corresponding revenue from the sales. So you have input and you have output. The graph shows an inflection point. Remember we talked about that. That's where we have a change in concavity. Well, if x is less than c, so somewhere on this side of the graph, you might notice that the graph is concave up, right? Which means that the rate of change of my slope is increasing. This indicates that the output is increasing at a faster rate with each dollar spent. So we're getting more revenue, more and more and more revenue each dollar that we spend, right? Which is good. But when x is greater than c, however, the graph is concave down, which means that the rate of change of our slope is decreasing. Now the graph is still going up, my revenue is still going up, it's just not going up as fast as it was before. My increase is slowing down. This indicates that the output is decreasing with each additional dollar spent. This means that value C produces a diminishing return. So that's the point, what we call, of diminishing return. That inflection point is going to be where it kind of changes concavity, or the point of diminishing return. Beyond this point, there is a smaller and smaller return for each dollar we invest. Let's do an example of that. Example number 6 says that we have a revenue function generated from the sales of a certain product. It's related to the amount X spent on advertising, and it gives you the equation here. It says where X and R are in thousands of dollars. Is there a point of diminishing return for this function? If so, what is it? So when I see this point of diminishing return, I know then that's when my function changes concavity, right? My point of inflection. I know that point of inflection is where my second derivative changes signs, right? And so let's go ahead and find the first derivative so that we can find the second derivative and find if there's any point of inflection or point of diminishing return. In this equation, you might notice that there is a fraction, a constant, just a number out in front. As long as that is just a number and there's no variable, remember we have a rule for derivatives that says that we could just keep that number chilling out in front and then just find the derivative of the rest of my equation. So the derivative of 600x squared minus x cubed is really 1200x minus 3x squared. That's my first derivative. Now let's find our second derivative. Again, I should be able to keep that number out in front as long as it's just a coefficient, and then I should be able to take the derivative of the stuff inside, which gives me 1200 minus 6x. If this is my second derivative, then I can take each term and set it equal to 0. Well, if 1 over 15,000 equal to 0 just kind of goes away. It doesn't give me an extra value. But I can take this 1200 minus 6x and set it equal to 0. I can solve, and I end up getting x equals 200. Remember, x represented the dollars spent in advertising, but remember it was in thousands of dollars. So when I get x equals 200, that really means $200,000 spent in advertising. So when we spend $200,000 in advertising, what's happening with my revenue? Well, let's look. Let's see if there's a concavity change. Let's see if there's a point of diminishing return, if I'm going to get less money in revenue as we continue to spend money in advertising. I'm going to take numbers and I'm going to plug them into my second derivative so I can figure out my concavity of this function. I'm going to test 100, I'm going to test 300, and remember we're testing it in the second derivative so I can see if the second derivative is positive or negative, concave up or concave down. Using my calculator, I'm going to test my second derivative, 100 in my second derivative, and I got a positive number. I tested 300 in my second derivative, and I got a negative number. That means I'm concave up and concave down. So just like the graph before, I was concave up, I was concave down. My revenue is going up, 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 up. It's still going up, but it's going up less quickly, right? And what is that point of diminishing return? Well, that's my point of inflection. So my point of inflection was at x equals 200, or remember, $200,000 spent in advertising. So I can say that the point of diminishing return is $200,000 spent in advertising. When I spend that $200,000 in advertising, what is my revenue? Well, if I want to figure out what my actual revenue is, I can take that 200, x equals 200, and I can plug it into my original revenue equation. Not my derivative, not my second derivative, but I can figure out exactly what my revenue is at that point, and then I know that my revenue might be going up, it's just not going to go up as quickly after that point. When I plugged in 200, I ended up getting 1066.666 repeating. And so what that means, remember, is it was in thousands. So if I add a couple more zeros onto there, if I add some zeros that I multiply by 1,000, that's 10, that's 100, that's 1,000. I think I added too many zeros, didn't I? So let's see here. I already rounded. If I didn't want to round, that would be 1,066,667 if I wasn't rounding, right? So I guess if this were repeating, then I can kind of round it to the nearest dollar, and I can say that we're getting $1,066,667 in revenue, but I had to put out $200,000 in advertising. But that's the point of diminishing return, where that revenue isn't going to go up as quickly from that point on. Okay? So point of diminishing return is kind of the same thing as our point of inflection on these functions.